In Chapter 4, we're first going to talk about determinants. You already know what the determinant of a 2 by 2 matrix is. It's the product of the diagonal elements minus the product of the off-diagonal elements. For this matrix, that means RU minus TS. And the reason determinants are useful is that if the determinant is 0, A is a singular matrix. It's only defined for square matrices. Determinants are only defined for square matrices, and only square matrices can be singular or non-singular. So at least for a 2 by 2, it's fairly easy to prove that if the determinant is 0, A is singular. And here's the proof. If we assume R is not equal to 0 and we reduce to echelon form, we knock out the element below by taking minus t over R times the first row and add it to the second to knock out this element. And this element ends up being U minus T over R times S. And this matrix is singular if and only if this is 0. And that's equivalent to saying that UR minus TS is 0. So if the determinant is 0, then this element will be 0, and you have a singular matrix. That's assuming R is not equal to 0. If R is equal to 0, that means you have to switch the two rows. So now you have the 0 here, and now the determinant is RU minus TS, but since R is 0, that's just minus TS. And if the determinant is 0, that means either T or S is 0. If T is 0, you have a column of zeros. If S is 0, you have a row of zeros. In either case, the rows or columns are dependent, and it's a singular matrix. So for a 2 by 2, the determinant tells you whether or not the matrix is singular. Now for a 3 by 3 matrix, the determinant is defined as follows, and you've seen this determinant used already in Chapter 2 in calculating the cross product. You expand along the first row, and it's A11 times the determinant of what you get when you throw out the row and column its own, i.e. this 2 by 2 matrix, minus, you always alternate in sign, minus this element times the determinant of what you get when you throw out the row and column its own, so that'll be this, plus A13 times what you get, the determinant of the 2 by 2 matrix you get by throwing out the row and column that it's own. So for example, this matrix, we'd have the determinant of A is 1 times the determinant of this matrix 3, 4, 0, 1 minus 2 times the determinant of 5, 4 minus 2, 1 plus minus 1 times the determinant of the 2 by 2 matrix you get when you throw out the row and column its own, 5, 3 minus 2, 0. Now since we know how to calculate determinants of 2 by 2s, we can calculate this, and we get minus 29, which means it is not singular because it's not 0. Now it's much harder to prove that the determinant being 0 implies that A is singular here. In general, it's true. It's not proven until the next section, which we're skipping, so we're going to skip the proof. You'll have to take our word for it that the determinant being 0 means the matrix is singular. So how do you define the determinant? Well, 3 by 3 is defined in terms of assuming you know how to calculate determinants of 2 by 2 matrices. Now what about a 4 by 4? Well, the determinant of a 4 by 4 matrix is, as you might expect, you expand along the first row, and it's this element 1 times the determinant of this 3 by 3 matrix minus, you alternate in sign, minus 2 times the determinant of the 3 by 3 matrix you get by eliminating the row and column that element's own, plus minus 1 times the determinant of what you get by throwing out the row and column its own, minus the last element, this, times the determinant of this 3 by 3 matrix. And now, since we know how to calculate determinants of 3 by 3 matrices, we can do this. So the determinant of the 4 by 4 matrix is A11 times the determinant of the 3 by 3 matrix you get when you throw out the row and column that element is own, and that's this 3 by 3 matrix. To calculate the determinant of that, we just talked about how to calculate the determinant of 3 by 3 matrix. You expand along the first row, 0 times the determinant of that, minus 2 times the determinant of that, 2 by 2, and so forth. And so since we know how to calculate determinants of 2 by 2 matrices, we know how to calculate determinant 3 by 3s, and now that we know how to calculate determinants 3 by 3s, we know how to calculate determinant of 4 by 4s, and you get the pattern. Here's the formula in general, and now you can get the idea that actually calculating the determinant of a 10 by 10 matrix would be a horrendous task, and in fact, using this definition, calculating the determinant of a 100 by 100 matrix is essentially impossible even with computers. So this is not a very practical definition for large matrices, but that's okay. We're going to use it for theoretical purposes and 2 by 2s and 3 by 3s mostly, occasionally a 4 by 4. But at any rate, one more time, the determinant of this 4 by 4 matrix would be 1 times the determinant of this 3 by 3 matrix that you get by throwing out the first row and first column, minus, you alternate in sign, plus, minus, 2 times the determinant of what you get when you throw out the row, second column and first row, and so forth. So you can define the determinant of 4 by 4 in terms of 4 3 by 3 matrices, and each of those 3 by 3s you calculate in terms of 3 2 by 2s, and horrendous task for large matrices, but that's how it's done. So one theorem in section 2 is that the determinant of a product is the product of the determinants. That's not proven here either until later chapter, but we'll use it in some of the problems. And the main, as we said, the main thing about determinants to know is that A is singular if and only if the determinant of A is 0. Now what chapter 4 is mainly about, though, is eigenvalues, and we've only talked about determinants because it's going to help us find eigenvalues. So what is an eigenvalue? If there's a scalar at lambda such that A has to be a square matrix, in this chapter all matrices are square. So if you can find a non-zero vector x such that ax is just a scalar multiple of x, then the scalar multiple lambda is called the eigenvalue, and the non-zero vector x is called the eigenvector. And it's important that the eigenvector is not 0, because if you allow eigenvectors to be 0, then a times 0 equals lambda times 0 for any a and any lambda, then all numbers would be eigenvalues. So x has to be non-zero, and by the way, it's not unique either, because you can see if you multiply x by 10 or 1/10, it still satisfies this. So the eigenvector is not unique. So we're trying to find scalars lambda such that ax is equal to lambda x. Well, that's equivalent to ax minus lambda x equals the 0 vector, or a minus lambda times the identity times x equals 0. And now if a minus lambda I, for any value of lambda for which a minus lambda I has an inverse, you can just multiply that by the inverse, and x will be a minus lambda I inverse times 0, which is 0. And so x would be 0, which means lambda can't be an eigenvalue if a minus lambda I has an inverse, because then the only solution x is a 0 vector, which isn't allowed. So we're looking for values of lambda for which a minus lambda I does not have an inverse, i.e. a minus lambda I is singular, which means the determinant of a minus lambda I is equal to 0, and that's why determinants are important here. So to find the eigenvalues of this 2 by 2 matrix, for example, we calculate a minus lambda I. That means you just subtract lambda from the diagonal, because identity is 1, 0, 0, 1. And this matrix must be singular. In other words, the determinant has to be 0. So you calculate the determinant, which is the product of the diagonal elements, minus the product of the off-diagonal elements. And you write that out, and you get a quadratic polynomial. And if you can factor the quadratic polynomial, you found the 2 roots. In this case, it factors as lambda minus 2, lambda minus 1. So 2 and 1 are the eigenvalues. And so those are the only values of lambda for which there's a non-zero solution to ax equals lambda x. Those are the eigenvalues. So in theory, this technique can be used to find the eigenvalues of any square matrix. For example, this 3 by 3 matrix, we're trying to find lambda such that a minus lambda I is singular and therefore has a zero determinant. So we subtract lambda from the diagonal of this matrix and calculate the determinant, which, as we know, is a good bit of work. But we know how to do it. It's this element times the determinant of that 2 by 2 minus 1 times the determinant of this 2 by 2 and so forth. And you end up with a cubic polynomial. By the way, they've expanded along the first column here. I haven't talked about that. Basically, the determinant of A is the same as the determinant of its transpose, and they saw they could make it a little simpler by calculating basically the determinant of A transpose minus lambda I. Anyway, if you do it the way we learned it, you'll end up with the same polynomial. It's a cubic polynomial. And of course, the roots of cubics are even harder to find. They're almost impossible unless you're lucky. In this case, we got lucky because lambda is a factor, so you can factor that out and then use quadratic formula, or in this case, actually factor the quadratic. In any case, in theory, you will always, for a 3 by 3 matrix, the determinant of a minus lambda I equals 0 will always give you a cubic polynomial. That's called the characteristic polynomial. And it's normally going to have 3 roots, which, by the way, that they may be hard to find for 3 by 3 or higher, may be very hard to find, but in theory you can do it. But notice that even though the matrix or matrices will always be real, so the characteristic polynomial will be real, the roots of a real polynomial can be complex. We're going to avoid complex roots for a while, but we'll deal with it later. All our examples will have real roots, but they could be complex. So in this case, we were able to factor it and find the roots are 2, 3, and 0. Now, triangular matrices, this one is lower triangular. That means everything above the diagonal is 0. They're particularly easy to find the determinants of. For example, this 4 by 4 triangular matrix, the determinant of t, you expand along the first row and you get A times the determinant of this 3 by 3 matrix, C0, 0, EF, 0, Hij, and the determinant of that, and all the other terms are 0 because you'll have, minus 0 times something plus 0 times something minus 0 times something. So you just get A times the term of this 3 by 3, and that's all. But now the term of this 3 by 3, you expand along the first row and you get C times the determinant of this 2 by 2. And the other terms are 0, minus 0 times something, plus 0 times something. Then the term of this 2 by 2 is Fj minus 0, so AC Fj, just the product of the diagonal elements. So a lower triangular matrix, the determinant is real easy to calculate, just the product of the diagonal elements. If it's upper triangular, well, it's proven somewhere in the book that the transpose determinant of a transpose is the same as the determinant of the original matrix. So if it's upper triangular, that's just as good. It's still the determinant is the product of the diagonal elements. That means that the eigenvalues of an upper or lower triangular matrix are extremely easy to find. In fact, we use that in our computational linear algebra course. We try to reduce a matrix without changing the eigenvalues to upper triangular form, because then you can just read the eigenvalues off the diagonal. Why? Because if A, for example, is this upper triangular matrix, then A minus lambda I, you just subtract lambda from the diagonal, and it's still upper triangular matrix. The determinant is just product of the diagonal elements, which would be 1 minus lambda times 3 minus lambda times 2 minus lambda times 3 minus lambda. And so you've not only got the determinant easily, you've already got it factored. In this case, it's the diagonal elements were 1, 3, 3, and 2. So you can just read the eigenvalues off the diagonal of a upper triangular matrix. Now the homework problems back in chapter 2, you have to calculate the determinants of some 2 by 2 and 3 by 3 matrices using the definition, expanding across the first row, just a straightforward exercise. Here you use the theorem that says the determinant of AB is equal to the determinant of A times the determinant of B to prove that AB is singular if and only if either A or B is singular. That follows directly from the theorem that determinant of AB equals determinant of A times determinant of B, and this one also comes from that, and so does this. The problems in section 4, we skipped 3, remember, are find the eigenvalues of a couple of 2 by 2 matrices. You just subtract lambda from the diagonal and set the determinant equals 0. You get a quadratic polynomial and find the roots. Those are pretty straightforward because you can always find the roots of a quadratic with the quadratic formula if you can't factor it. The 3 by 3 ones are, you end up with a cubic polynomial, and you have to be lucky or something to find the roots of that, but you will be lucky on these. And the problem 28 is particularly interesting because it's a practical way of finding at least one eigenvalue of a large matrix. So we said for a large matrix, even a 10 by 10, trying to find the eigenvalues using the technique we've been talking about, subtracting lambda from the diagonal, calculating the determinant, which is a humongous task. Then you got a 10 polynomial degree 10. It's hard to find the roots of that. But this is a much better way for large matrices. It's a very simple method. You just take a non-zero vector and start multiplying it by A, and eventually every time you multiply it by A, it multiplies the x by a scalar, namely the largest eigenvalue of A. So you can find the largest eigenvalue of A iteratively, and you're supposed to try it with this problem.